The next part, we're going to talk about sensors used in robot. So there are many kind of sensors we can use in robot. The major detection we need to do is to detect the angular movement of joints, the distance between the robot and the surroundings, and the distance between the target object and, the robot itself. There are many sensors we can do for those kind of activities. We can use resistive sensors, like we can detect the bending of a joint. We can use tactile sensors. It may be resistive, it may be capacitive, it may be other type of sensors. We can use infrared to detect the distance between two objects, or use ultrasonic sensor to do the same thing. In order to detect the motion, acceleration, velocity, those kind of properties, we can use inertia sensors or use other accelerometers, those kind of sensors to do those kind of things. If you are dealing with mobile robot, we might need to use laser range sensors to detect what's going on around the robot itself. We might need to use GPS or other vision sensors to detect where I am or where I need to go. So those kind of things are the common sensors used in a robot. So as you can see in this picture, there are many type of sensors you might need to deal with. Depending on what kind of application you're targeted, you need to select the corresponding sensor. It may be chip type, it may be resistors, it may be some kind of electronics, or it may be just a mechanical switch. Anything that fit into your application, you can just select the one. But keep in mind, resolution is one of the important thing. You will need to uh, find the correct sensor that fit into your applications. If you cannot find the correct sensors, you might need to consider use sensor fusion to fuse all the measurements all together and find out the correct mathematical representation of the information so that you can get everything correctly. Let's talk about resistive sensors. So resistive sensors is simple because the output is resistance. By detecting the change of resistance, we should be able to find out what physical properties has been changed. So let's talk about different type of things. The first one we're going to talk about is bend sensor. So bend sensors is pretty straightforward. The bend sensor is going to look like this. For this kind of sensor, if you see from the side, when it's not deformed, you got to get one resistance. But as soon as it start to be bended, the resistance is going to be changed. So if we can detect the change of resistance, we should be able to find out how much bending the sensor is being bended. So in that case, we can determine what is the angle of uh, of the device has been uh, changed. So if we are using this kind of sensor on a robotic device, one of the example is that if we put that on a finger, let me change the color of the pen so you know what's going on over here. So let's say if I have a sensor that has been bended over here. So since this one over here has angle change, so you might detect what is my delta R. If the delta R is identified, then we should be able to detect what is the change in terms of angle. So this is something we might be able to identify the angle of a robotic device. And that is a very common application that we can use for this kind of sensor. The other one is potentiometer. So for potentiometer, just look at the configuration over here. Clearly, this one is going to be a rotary detection. So when it starts to be rotated, the resistance is going to be changed. The advantage of this one is this sensor is that it can be equipped at robotic joints. That is, the movement is going to be angular movement. So again, this is easy to be purchased, and this is easy to mount, and the price is pretty low. So it can be a very good sensor for robotic devices. However, one of the major drawbacks is that the change of the resistance sometimes is not linear. So if you say the angle change from 0 degree to 45 degree, it doesn't mean from 0 degree to 90 degree, the change of resistance is going to be doubled. Instead, depending on where you rotate your potentiometer, the resistance need to be mapped into a specific location. In other words, the sensor output is not a linear one. So when you have a nonlinear sensor, you might need to build a map to map from the beginning till the end and detect what is the limitation or the range of this sensor. So sometimes it can be a little bit tedious for us to identify. And if you change the potentiometers, it doesn't mean it's going to have the same output. So we probably want to keep the sensor as the same type all the time so that we do not need to change the programming code in our control algorithm. That is one thing that we might need to worry about. And the third one is a light sensor. Sometimes we call it photoresistor. This one over here, the resistance, it looks like there is a curve on the surface of a plate. And for this kind of things, the resistance of this sensor is going to be changed based on how much light has been received. So if we try to detect what's going on in the environment, this can be a very good device to detect whether we receive a light or we are working in a very dark room. This one is very good to detect what is my current direction. For instance, if you need to drive your robot toward to a light source, and then this kind of sensor is going to be extremely good for this kind of application. You might need to uh, change the direction of a solar panel. So we always point our solar panel to the direction where the sun is located. So in that case, if we can have our photoresistors located on the panel, then we can always detect what is the maximum luminance so that the solar panel always pointing to the direction to the sun. So we can always maximize the output of our collectible energy. So that is going to be used in that kind of application, pointing to a light source and use that to optimize or to ensure the device is always pointing to the light source. Now, what kind of applications that we are going to use? So I'm going to talk about two different kind of applications over here. The first one is we probably want to find out the angle of a robotic device. So we can use either the bending resistance or use the potentiometers to do the job. If we are using bending sensor, then you probably just attach this one on the surface over here. So when you change your orientation of a specific joint, the sensor is going to be bended accordingly. So by knowing the change of resistance over here, we should be able to know how much angle between the first link 1, and link 2. That's probably something we can use for this kind of application. The other application that we're going to, the other type of sensors we might be able to use is, since this one over here is a joint, then we probably put a potentiometer or a pot over here. So when it starts to be rotated, we can measure the output voltage and ensure what is the angle the potentiometers has been rotated to. However, keep in mind, let me repeat it again, the output of resistance might not be linear. So if it's not linear, how are you going to convert the angle, convert the voltage or the resistance into the information of angles? That is something we might need to consider. So when you are using those kind of things, we might need to use a table, lookup table, to determine what is my current angular position. The other one is we can use this kind of sensor to serve as a weight sensor, which is pretty straightforward, just like what you see over here. So if this one is a bending resistance, bending resistive sensor, then let me draw in this way. We put a spring over here. So if we got the force, then the sensor is going to be bended. So we should be able to detect the change of resistance or delta R and determine how much deformation of this thing has been created. So we can determine how much force has been applied in this direction. Once the force is removed, the spring is going to push everything back to its original position. So if we know the delta R, or we know delta X, then we should be able to determine how much force has been applied to the specific structure. Those are the things that we might be able to use with resistive sensors. The other thing that we are going to talk about is driving circuits. Since we are talking about resistance, it means that we cannot use microprocessor to detect the change of resistance directly, because for most of the microprocessors, we can only detect either it's going to be current or it's going to be voltage that can be tagged into as an input signal for our microprocessors. So with that case, we need to find out how are we going to change the resistance, or how to convert resistance into voltage. We can just use a voltage divider. The idea is pretty simple. We got our Vs, or the power supply over here, and on the other side is going to be ground. We would need to use, in this case it's R2, or this is a carrier. And this one is R1, or sensor. This is going to be your output voltage. Why can we do that? So the sensor over here is changing, because depending on the physical properties, the resistance is going to be changed accordingly. So since we know this is going to be changed accordingly, the Ohm's law of this circuit is going to be written in this format. So we got two resistance which means the total resistance is going to be R1 plus R2. R2 is my carrier resistor, so it's going to be a constant. But I put something like this, the V out or V sense over here can be a ratio by using R1, R2, and the input voltage. So if you can use this equation over here, you should be able to find out what is my current resistance. And this has been used in many resistive type of sensors in the past few decades. Another one is sometimes the change of the resistance of the resistive sensors is pretty tiny, and it might be difficult for us to detect the slight difference due to the change of the sensor. So we might be able to use Wisdom bridge. So all the R are going to be the same, but the sensor is going to be R plus delta R. So the output over here, because the signal is pretty tiny, even though with Wisdom bridge, we should be able to detect the difference or the resistance change of the sensor, but it can be a good idea that we just adopt operational amplifier to amplify the output between the two ends. Obviously, this is going to be this side is going to be 1/2 V, and this side over here is going to be a little bit low. It's close to 1/2 V, but because the delta R over here has been changed, so this side over here is no longer R plus, is no longer 50%. Instead, depending on how much resistance is changed due to the physical environment conditions, then we might need to write this part accordingly. However, keep in mind, sometimes those kind of a signal, the change of the signal might be extremely tiny, maybe only a few millivolts, and on the other side, it might be 112 volts. So when we are dealing with those kind of things, it is necessary to amplify the amplitude from a tiny one into a big one, because the difference between those two ends might be just like 1 millivolts or 600 mu volts. So we might need to amplify the signal from the smaller one into a bigger one. So that's the reason we got an operational amplifier over here. And if we can put some kind of binary threshold over here, the same circuit can be used in digital control and control some devices accordingly.